So now we are going to do chapter 19 review. In this case, as I recall, we have 5 questions. And so first one is naming, how to name individual compounds. And I noticed I will have to fix this. It's corrected in the answers, but I forgot to fix that here in the actual questions. I didn't want, if you look actually this compound here that is error is not actually such a bad error. But if you look at this compound, how would you name it? Can somebody tell me what would be parent compound? Parent molecule or root of the name? Yeah, go ahead. No, it's not benzene. That's actually, I wanted it to be benzene, and then when I realized it's not benzene, I changed it to benzene. So, yeah, go ahead, somebody at the back. No, it's the double bond that is the problem. So yeah, go ahead. No, it's styrene, actually. Yeah, benzene with double bond is styrene. Yeah. And so when I realized that's the case, I decided I'm going to change it. So, okay, let's look at the answer. So this would be, you would name this as styrene. And so this would be carbon 1, carbon 2, and carbon 4. So 4-bromo isobutyl styrene. Yeah, styrene somehow is a little bit complex, and yeah, so I will fix that. So students somehow have difficulties remembering. So let's look at the actual ones that I intended. Because this may be a little bit challenging. There will be definitely nomenclature questions on the test, and they may be both ways. Write-in questions where you have typed in the actual name, or multiple choice. And you can expect both, and you can expect several nomenclature questions. I don't know how many, but you can expect several. And so they will be different level of difficulty. Maybe very easy, but also quite challenging. And so these ones are a little bit more on difficult side, a little bit more challenging. And so here is how you approach that systematically. First, you look at benzene ring, and you first name each substituent. So you should have pen and paper, and simply write down on paper name of each substituent. So just go around the molecule and you name them. This is bromo, this is isobutyl, maybe a little bit difficult to recognize, but it's isobutyl, 4 carbons, that's butyl. On carbon next to last there is branching, that's iso, so isobutyl. And this one is allyl, double bond separated by 1 carbon from rest of the ring. So you have bromo, isobutyl, allyl. And you don't have any more, so root is going to be benzene. And when you list them alphabetically, it's going to be allyl, bromo, isobutyl, benzene. And now the only question is, what is the numbering? And so in this case, it's the smallest possible set of numbers. That's 1, 2, 4. And then you see which number is associated with each of the substituents. That's 1 allyl, 4 bromo, 2 isobutyl benzene. And then you repeat the same process for the next one. But now when you're naming substituents, let's say you start here, it's chloro, it's nitro, and then you have methoxy. Hopefully you would remember that methoxy on benzene ring, that's anisole. Hydroxy is phenol, amino is aniline, carboxyl group is benzoic acid, sulfonate group is sulfonic acid, double bond styrene. Those are ones you have to memorize. You cannot reason those out. You just have to memorize them. And so hopefully we recognize this as anisole. And so you're naming this as anisole, which right away fixes this carbon as carbon 1. This has to be carbon 1. And you don't list that one in the name. Because by naming this anisole, you have indicated that one substituent is methoxy and it's attached to carbon 1. And so the remaining 2 substituents get the smallest possible numbers, which in this case are 3 and 4. And so it's 4 chloro, 3 nitro. Again, you list them alphabetically. So 4 chloro, 3 nitro, anisole. And then the last one. So you name substituents ethoxy. I intentionally used ethoxy here as difference from methoxy, because methoxy gives this ring a name, so it's another parent compound, anisole. But with ethoxy, ethyl oxy, when you have alkyl group and oxygen, that's that alkyl oxy, alkoxy group. So in this case, ethoxy. That's just ethoxy group. You just name it as any other substituent. So now it's a benzene ring. So you have ethoxy, you have iodo, and this is cyclobutyl. Don't be confused by rings. Rings, you simply use prefix cyclo and then whatever number of carbon atoms you have. 3 propyl, cyclopropyl, 4 cyclobutyl, 5 cyclopentyl, 6 cyclohexyl, and so on. And cyclo is alphabetized. So the order of substituents is going to be cyclo, ethoxy, iodo. And then numbering is the smallest possible set. And in this case, numbering is in alphabetic order because it's 1, 3, 5 substitution pattern. You can start on any of these 3 substituents. And so when there is a tie, you start at first this is substituent, 1. And so you assign 1 to cyclobutyl. And now which one is going to be 3? Well, you can number them clockwise or counterclockwise. So either of the two could be 3. So next listed gets next smallest number. That's 3. And then 5. So these are 3, I would say, patterns of nomenclature that you should be familiar with. There could be, of course, more, but these are kind of 3 patterns that you should be familiar with, and how to systematically approach nomenclature so that you can name compounds correctly. Any questions? Yeah.
Does the numbering have to match the alphabetical order in this case? Like 1 is the first letter.
Yeah.
That goes
135, yes. In case 135, yeah. Yes, it does. Now, of course, you can always ask questions after. Question number 2. Are the following compounds or ions aromatic? For each one, determine the number of delocalized pi electrons and Huckel N number. So first compound is imidazole. And you have to determine which electrons are delocalized of the free electrons. So in this ring that's imidazole, you have 2 pi bonds. Each has 2 pi electrons, that's 4 pi electrons. And now we have 2 free electron pairs. We need to know whether none of them is delocalized, one is, or both are. This free electron pair is on carbon that forms only 3 single bonds. So that free electron pair will be in unhybridized p orbital. This is actually going to be sp2 hybridized nitrogen. We covered that in the class in detail. You cannot know that in advance, but and that's one of the weaknesses of valence bond theory and resonance concept. But in this case, for this electron to be delocalized, it should be in atomic p orbital, because then it overlaps nicely with molecular pi orbitals and is delocalized. So this is delocalized free electron pair. But the other one is not. The reason why it is not is that this nitrogen already forms a double bond. It could have only one atomic p orbital, unhybridized p orbital, because by forming double bond, it's sp2 hybridized. And so there is only one unhybridized p orbital left, and that one is after hybridization. And that one has been used up for formation of double bond. That means that free electron pair is in hybrid sp2 orbital and cannot be delocalized. Electron pairs in hybrid orbitals are not delocalized. That means that only one is delocalized, the other is not. So one counts towards the number of pi and p electrons. And so we have this electron pair, 2, and then 2 pi bonds, 4, 6. So 4n plus 2 equals 6. That we saw that for n, Huckel number n is 1, and that means this compound is aromatic. Any questions? Okay. So let's look at the next one. So next one, a little bit odd compound. It's a cation that also has oxygen with 2 free electron pairs in a ring. We have, of course, carbocation, which means an empty p orbital. So electron delocalization is possible through that cation. And of course, we have pi electron pair. And the only question is about these two free electron pairs. So following reasoning we had before for this nitrogen, this oxygen forms only two sigma bonds. That means that one of the electron pairs is in unhybridized p orbital. The other one is not. The other one is in hybrid sp2 orbital. So oxygen is sp2 hybridized, and one electron pair is delocalized. The other one is not. But if one is delocalized, that means we have a total of 4 pi electrons. And that means 4n plus 2 is 4, n is 0.5, 1/2, and that's anti-aromatic compound. So this compound would be anti-aromatic. Electron delocalization actually destabilizes this compound. So for that reason, it would attempt to avoid electron delocalization. In this case, it's difficult to avoid it because molecule has to be planar. I don't know exact properties of this compound, but analysis that we have covered in the class so far would point to it being anti-aromatic, so destabilized by electron delocalization. Any questions? Okay, so next one. Again, we need to count p and pi electrons. And so let's look at pi. We have 1, 2, 3, 4, 5. 5 pi bonds, that's 10 pi electrons. And on nitrogen, there is nothing shown. But we don't have to show you free electron pairs. You should know at this time. And in general, when representing organic molecules by condensed formulas like these, we don't have to show free electron pairs. We often show free electron pairs as a courtesy to the reader, but we don't have to show them. We assume that a chemist would know that if there are free electron pairs present. And so you should know that nitrogen has 5 valence electrons, so 3 are used to make each of these single bonds, and so 2 are left, and they are here left as a free electron pair. That means 2 more electrons. So total of 12. Of course, it forms only single bonds. And that means that this free electron pair would be in unhybridized p orbital and delocalized. And so total of 12. So 4n plus 2 equals 12. N is 2.5. So this would be anti-aromatic if molecule is planar. This is a little bit larger molecule. And even though individual double bonds are planar, it is possible that this ring would attempt to twist to avoid planarity and avoid electron delocalization. Because anti-aromatic means that molecule or species, ion, for example, is destabilized by electron delocalization. And so when we count double bonds, there are 1, 2, 3, 4, 5, 6, 7. 2 electrons in each, 14. So 4n plus 2 equals 14. That we solve that for n, that's 3. So this is aromatic species. Okay, so any questions about number 2? You can expect that you will have to do analysis like this and calculation like this on the test. Next one, number 3, is draw molecular orbital diagram of cyclopropenyl anion. Is it aromatic, anti-aromatic, or simple alkene? Simple alkene is one that may have more than one double bond, but is not delocalized. Electrons are not delocalized, like cyclooctatetraene. So you use this mnemonic to identify energy levels, where you draw, since it's cyclopropenyl cation, that's actually a 3-membered ring with a double bond. And then you have a cation there. So if it's 3-membered ring, you draw a triangle with one corner pointing down, and energy levels are at the corners. And then energy level of 0, which distinguishes which orbitals are bonding, and anything with energy below 0 and anti-bonding. So that level is set so that approximately bonding and anti-bonding, when you add up those, if you were to use some numbers here, they would end up overall being about 0. So how many pi electrons we have? We have 4. The way to figure that out is that cyclopropenyl anion has a double bond. So there are 2 pi electrons from double bond, and then anion carbanion means that there is free electron pair on the carbon. So that free electron pair are 2 more electrons, total of 4. Another way to look at it is simply consider cyclopropene or the localized species that has 3 carbons. So 3 carbon ring that is delocalized. Each carbon would contribute its p orbital and 1 electron. That's 3 electrons. Plus 1 electron for negative charge because it's Ni. And that will be 4 electrons. First way of counting 1 electron pair from a pi bond and another free electron pair is usually easier. Either way, 4 electrons. And if you draw energy levels correctly, so triangle for 3-membered ring with 1 corner pointing down, and then you distribute 4 electrons. 2 electrons are paired up in low energy orbital, bonding orbital, and then remaining 2 electrons, following Hund's rule of maximum multiplicity, fit 1 per orbital. And that's it. We don't have any more electrons, which indicates that this is a diradical. So this species is unstable, and it's actually anti-aromatic, because in ground state, it has 2 unpaired electrons. So this is an anti-aromatic species, and it's destabilized by electron delocalization. Now, it's important to keep in mind that it is anti-aromatic because it has these unpaired electrons in degenerate orbitals. Degenerate are orbitals of the same energy. It's not anti-aromatic because it has electrons in antibonding orbitals. It doesn't matter. It just happens that these are antibonding orbitals. It just makes it even less stable. But as long as there are unpaired electrons, that's anti-aromatic species. So unpaired electrons in molecular orbital diagram means anti-aromatic species. Any questions? Question number 4. Which of the following is suitable catalyst for the reaction below? And so you have a reaction where benzene reacts with 2-chloropropane to give propyl or isopropyl benzene. And so catalyst. What is catalyst? Well, if you have studied this, you probably recognize this reaction as Friedel-Crafts alkylation. Catalyst in Friedel-Crafts alkylation is Lewis acid. And so you simply rephrase this question. Question is really which of the 4 is Lewis acid? Because Lewis acid, any Lewis acid will catalyze this reaction. And so when you consider first one, phosphorus trichloride, again, we don't have to show free electrons, but phosphorus has 5 valence electrons. 3 are used to make these bonds. There is 1 free electron pair. This is actually, there is free electron pair on phosphorus. That's actually Lewis base, not Lewis acid. There are some ways where phosphorus could act as Lewis acid, but pretty weak in this particular one. Zinc chloride, that's actually Lewis acid, and that's good, strong Lewis acid that would work in this case. So that's correct answer. This sulfur dichloride is also not suitable. It's also a Lewis base. And potassium chloride is not a Lewis acid because potassium has no tendency to accept electron pair. So correct answer is B. Simply you have to be able to identify Lewis acid. And question number 5. What is the product of the following reaction? So here we have reaction of benzene ring, cyclopentanol, and catalytic amount of sulfuric acid. So first you have to consider what sulfuric acid does to cyclopentanol, because catalytic amount of Lewis acid in benzene you wouldn't expect really much, and in general they don't react. We need fuming sulfuric acid to sulfonate benzene. Otherwise, like ordinary sulfuric acid, they can use to purify benzene to remove impurities from benzene. So sulfuric acid dehydrates, basically it protonates hydroxyl group, and then molecule of water is lost. So it basically effectively dehydrates this resulting oxonium ion to give corresponding cation. So You should remember that from chapter 15. So actually, in this case, reagent is cyclopentyl cation. And then you may remember that Friedel-Crafts alkylation is reaction of corresponding alkyl cation with benzene ring. And here is complete mechanism that includes cyclohexadienyl cation. So pi electron pair forms a bond with cyclopentyl cation that results in formation of intermediate cyclohexadienyl cation, loss of proton, regenerates benzene ring, and product is cyclopentyl benzene. So this completes review of chapter 19.